Hello, my name is Alec Hegg. I am a senior graduating with a degree in chemistry, and I'm going to be talking today a little bit about my honors research in Professor Hoyt's lab on the isolation of reduced iron hydrosilylation catalysts. Catalysis is used as one way to increase the sustainability of some of our chemical processes, and hydrosilylations in specific are the addition of a silicon and a hydrogen across a double bond. And so these products that are formed as a result of hydrosilylations have a lot of industrial uses, which I've shown below. And the Hoyt group over the years has developed a number of hydrosilylation catalysts that are all based on this core structure, but that differ in the identity of these aryl substituents. Now, those structures that I showed before are actually inactive pre-catalysts, and in order to perform the hydrosilylation reaction, we first have to perform this activation step, where we reduce the two bromines off of iron to open up that coordination site here where our substrates can come in and bind to iron in order to give us productive catalysis. When we do this reduction, we see that we have a wide range of yields, and those yields are depending on which pre-catalyst we start from, so which aryl substituents we have. And it would be very easy to say that the steric effects from the different substituents on these aryl groups is what's deciding the yield. But another possibility is that we're not having full efficiency of this first reduction step. And so one way that we wanted to test which of these is actually the cause of our disparity in yield is to make some catalysts that are pre-activated but bound by a ligand here to stabilize that iron state. And then we could test that in our hydrosilylation reaction and directly compare between the in situ reduction and the pre-reduced species. Over the course of this year, we succeeded in making these two reduced iron species, the toluene and cod being those binding ligands, and we were able to characterize these to get a bit of a better understanding of their structure and reactivity as well. We also showed that that toluene activated complex was active in the hydrosilylation reaction, giving us a 98% yield, which compares very well to the in situ reduction method, which had a 99% yield. And this is a really favorable indication that our methodology may work in order to compare yields between those in situ and pre-activated catalyst designs. Lastly, I'd like to thank the Hoyt Lab Group, Chuck Schultz, the Knox Chemistry Department, and the Richter Fund for funding my research. And thank you all for listening.